Hello everyone. Good morning to the topic from design and analysis of algorithms, that is Master's Theorem. This technique basically helps you to analyze the time complexity of multiple recurrence relation or recursive functions. So basically Master's Theorem can be implemented only if your recurrence relation is in the form of t times n is equals to a times t n upon b plus theta of n to the power k log to the power p n, where a should always be greater than equals to 1, b should always be 1, and p is some a real number. So only if the recurrence relation is in the form of this, then we can apply the Master's theorem. Let's say if I tell you an example is t of n is equals to 2 times t n by 2 plus n. So type of this recurrence relation, you can implement the Master's theorem. But if in case you have any recurrence relation, like say 2 times t n minus 1 plus some function of n, let's say n square. So in this type of recurrence relation, you cannot apply Master's theorem because you don't have any p which is greater than 1. So the recurrence relation where you can apply the Master's theorem, I think it is clear to all of you. Now, there are three rules that you have to follow while you are applying the Master's theorem. First of all, just calculate the two terms. First term is calculate A, which is already given, and second is P to the power K. So you just have to calculate these two values, and all the three cases will be followed with these two values. Is in case, as the formula says, that if the value of A is greater than P to the power K, then your time complexity will be simply theta times n to the power log A to the base B. So whatever will come here, that will be taken as time complexity. For example, let's say if you have the recurrence relation t of n is equals to 2 times t n by 2 plus n, where a is equals to, in this recurrence relation if I see, a is equals to 2, b is equals to 2, and let's say here we don't have any k which is equals to 1. Let's say we can say that let's say a is equals to 4. Let's say this is 4. So a is 4, and now you have a which is 4 is 2 to the power 1 which is greater than. So it satisfies the rule number 1, which is a is greater than b to the power k. Here k is equals to 1. Okay. So the time complexity t of n will be theta of, you just have to write simply the values of all the terms that is given here. Theta of n times, let's say, log a, which is 4 base 2, which is b. So theta will be what is n square, because log 4 base 2 is equals to 2, so it will be n square. So simply the time complexity is n square. So this is how you can apply Master's theorem on this kind of recurrence relation. Let's say if you have a is equals to 2, which was the previous recurrence relation, let's say t of n is equals to 2 times n by 2 plus n. Here a is equals to 2, b is equals to 2, and k is equals to 1. That means you have a recurrence relation which is 2 is equals to 2 to the power 1, which is k. Now it lies in the case number 2. Then you have to check what is the value of p. In this case, the value of p is equals to 0, which is greater than minus 1. So the time complexity will be t of n is equals to theta of n to the power, what n to the power? Log a, which is 2 base 2, which is b, and you just have to write log 0 plus 1. The value of p is 0, and you have to write n here. So the total time complexity is theta of n, which is 1. Log 2 base 2 will be 1. N log n. And this is also the recurrence relation of your merge sort. Okay. So this is how you can satisfy the case number 2. Again, let's say if you have some recurrence relation which comes with, let's say, t of n is equals to 2 times, let's say, let's say you have some recurrence relation t of n is equals to 2 times t n by 2 plus n square. Let's say you have some recurrence relation like this. So Here a is equals to 2, b is equals to 2, and your k value is also 2. That means a which is 2, b which is 2, k to the power k is equals to 2. That means you lie in rule number 3. So you have to check the value of p. Here p is also 0, which is greater than equals to 0. Then time complexity t of n will be theta of n to the power k. K is 2. Log p is 0. So it will not have the term of, you can say, log, which is 0 and n. So the time complexity will be theta of n square. So this is how you can implement the Master's theorem on different recurrence relation. But let's say there are some exceptional cases also. If you have any recurrence relation, let's say given like this, 0.5 t of n by 2 plus n. Let's say you have any recurrence relation like this. So here a is greater than equals to 1 condition is not true. That means you cannot apply Master's theorem on this particular recurrence relation. Let's say you have some recurrence relation t of n is equals to 2 to the power n t of n by 2 plus n square. Here also you cannot implement the Master's theorem because you don't have a as a constant, you have a as a function of n, which dissatisfies the condition of Master's theorem. Let's say if you have any recurrence relation t of n is equals to, I have already told you that t of n by, let's say, 1 or no n here, plus let's say n log n. So here also you cannot apply the Master's theorem. So there are some exception cases also where you cannot apply the Master's theorem even if you have the recurrence relation is in the form of a t n by b plus theta of f of n, function of n. So in some cases or some books you can see here it has to be like this: t of n is equals to a times t of n by b plus function of n. So this f of n and theta of n to the power k log to the power p n is also same. So you can you can see both the cases. So it is all almost same. It is same. But you have to be very clear with the conditions. You have to be very clear with the conditions that h should always be greater than equals to 1. You cannot even take a as in you cannot even take some value 0, b you cannot take 0. You have to be greater than 1. Means you should have something in denominator and you should have something greater than equals to 1 into numerator. Then only you can apply the Master's theorem. So this is the simplest method to apply. This is the simplest method to analyze the time complexity of any recurrence relation. Thank you so much.